Welcome. I want to say three things, short remarks. One I already addressed, but it's such a beautiful day with foliage and the colors and the trees. It's nice to talk about trees and colors. And this foliage inequality is about that. I already mentioned it. It's something, a remark relating the arboricity of a graph, for general relation between the arboricity and the acyclic chromatic number. So there are interesting quantities for graphs, which one also can look at on the subclass of manifolds. But in general, one has this relation, and this relation generalizes a relation which has been known since 1994. And I explained this already a little bit. I'm writing this down. It's a short note which explains how these Kempe chains can be used for building the trees. So when you have acyclic coloring, then this means that the Kempe chains are forests, and then you can just put them together. You can pair them and get, in the even case, even a little bit the better results than what was known. The second remark is triggered by the math table talk of Daniel Sheremata this last Wednesday. He talked about peg solitaire on graphs. It's an interesting problem. So as a kid we had played that often. This is a peg solitaire. You have to jump over a neighboring peg, and then you take it away, and so on. In the end, you want to achieve that all the pegs are gone. And my remark here is just that it's obviously easy to do if you have a Hamiltonian path, because then you can reduce it to a one-dimensional situation where one knows if there's an even linear path or cyclic path, then the peg problem can be solved. And since D manifolds in general are Hamiltonian, this generalizes a result of Whitney and Tutte, and we have, which is kind of a nice construction. It's actually constructive. What you can do enough unit spheres, and if you pack it with unit spheres, then you make sure that you make a detour to get to the center, and then you have also to link the different Hamiltonian paths which you have on the d-1 dimensional subspace, and to get the Hamiltonian path on the whole manifold. It's a Swiss cheese proof. But once you have that Hamiltonian path, then if it's an even length, then you have immediately solved the solitaire. So that's about the peg manifold. Another thing I wanted to these functioners are very important in complexity theory. So there's a nice movie which I have in my math in movies collection, Traveling Salesman from 11 years ago, and it's a kind of a Dürrenmatt type story. There's almost nothing happening. There are just people discussing on a table, and like in Dürrenmatt's play. And in Dürrenmatt play, of course, the atomic bomb was the big deal, right? Physics losing its innocence with the atomic bomb. Oppenheimer is mentioned in this movie, and now it's no more chemistry or physics which is decisive, but the mathematics. And
what if I melted the sand? Took all the sand in the desert and melted it. Glass. The whole desert becomes one big sheet of glass.
And this reminds me, when I look at manifolds, the big questions like Hamiltonian, whether the graph is Hamiltonian or not, or whether it's recolorable or not, or what is the chromatic number, or how many clicks there are. These are, or the peg solitaire on a manifold. It's relatively easy.
Because it's a different problem.
That's utterly ridiculous. We're not even talking cutting-edge theory here. Gary, Johnson, guys in the 70s showed that fundamentally all these complex mathematical problems, knapsack, sat, whatever, they're all the same problem.
By the way, I borrowed the book from the library, Computers and Intractability by Gary and Johnson, which is also mentioned in that movie, and it explains also things we kind of bother with when we are doing calculus, like what is the difference between polynomial and exponential. So when you look at polynomial tasks, this takes a fraction of a second, and in this table here it shows then kind of if you have an exponential thing, you might need 10 to the 13 centuries to solve the problem. So there's a big difference between polynomial and exponential, and that's what P and P is essentially about. And just formulate, this was the first time that was boiled down to earth problems like the three-colorability or the Hamiltonian property. And so if you melt the sand, somehow when you are looking at manifolds, where there's a nice crystallinic structure, then the problems become easy. First of all, the click problem is easy because of just the dimension is bounded, that the colorability is easy. That's Heawood's idea. So on spheres, you can immediately, also in general dimension, arbitrary dimension, you can just see whether you have a minimal coloring or not. But the Hamiltonian problem can be done also recursively, kind of delegated to the spheres and then put together. And the text solitaire problem then also can be solved quickly on a manifold. And that's all what I wanted to say today.